So let's continue with our study of velocity-dependent effects in, in relativity. And the next one we're faced with in our special topic C is called Gravito magnetism. Okay, we've seen elements of this in the lens tearing effect, and now we want to take a second look at it. Okay, and see that gravitomagnetism, by virtue of being a special relativity effect, is very familiar to us and resembles uh, the magnetism of electromagnetism. We made the point in the last lecture that when we look at weak gravitational fields, okay, and then put test particles into them that are non-relativistic, we expect to find effects that are proportional to the non-relativistic velocity of the particle, and we expect those effects to look like magnetism. Okay, they should look like magnetism, except the charge should be replaced by the mass. Okay, and the coupling constant should be replaced by Newton's constant. And we notice that simply because in this kinematic situation, okay, we can treat the mass of the particle as invariant, okay, because we're only looking at small velocities. So although the mass of an object in relativity is the fourth component of a 4 vector and has and transforms from frame to frame, if we're restricting ourselves just to low velocities, we can treat it to sufficiently high accuracy as a constant. Okay, the other, and then we also saw, okay, that the source of the gravitational field reduced from a 10 component tensor down to a 4 component vector, and it looks just like electromagnetism. Okay, so a lot of the formalism will be that of electromagnetism and simply relabeled. Okay, this is not a deep connection between electromagnetism and gravity, okay? This is just the fact that we're making two approximations that throw out the differences between the two theories. Okay, I hope I've made that clear. That's certainly clear in the formulas. And the next topic we're going to take up is to look at strong gravity and the rotating black holes, okay, where the differences are dramatic indeed, and that's really where we're headed, and we're more interested in it. So I'm using general relativity formalism for a problem which is really just special relativity. But let's see how things go. Let's derive things in this language to get used to this language so that we can handle a new problem, the Kerr metric, the metric of a rotating black hole with additional confidence. So at this point, our metric was just shown here in the case of weak gravity for slowly rotating stars, with good enough accuracy for me to discuss slowly moving particles. Okay. Okay, so here's my metric, and then I can ask, well, what about mass points? I discussed how gyroscopes work in this environment, how they travel parallel, transported along the paths of their bodies, okay, of their mass points. But what about the mass points themselves? Well, of course, they satisfy the geodesic equation, which I've written down here. And let's work on that geodesic equation, simplify it, and see that it's an old friend of ours. Okay, okay. How do masses? We're asking the question: how do masses move in a gravitational field where the field is weak, and the motion of the particle is essentially non-relativistic? Okay. Well, okay. Let's take a look. Let's see what happens. Let's clean up all this stuff. Okay. So here's the 4 velocity, and here's the Christoffel symbol. For non-relativistic motion, my 4 velocity simplifies, as shown here. Gamma is essentially 1 to second order in V over C. I'm working to first order in V over C. The difference between proper time and ordinary time in an inertial frame is also second order in V over C. Okay, so I can drop that as well. Oh, so I'm getting away with murder here. What's going to be left over? Well, we'll see. The geodesic equation then reduces down. Okay, so I'll just take a spatial component of the velocity. So I have d by d tau applied to d by d tau on x, the position, to get putting this into this equation. So the left-hand side just becomes this, where xi is the ith component of the position of the particle, and on the the Christoffel symbols simplify, okay, because I'm looking only to first order in velocities, so I'll get a term where alpha and beta are 0. I've written that out. In that case, the u's are simply c's, so I get 2 of them. I've thrown stuff on the right-hand side of the equation, so I get a minus. And then I get the additional contributions when alpha is 0 and beta is I, or when beta is 0 and alpha is I. Okay, and so I've written those down here. Okay, so one of the lower indices on the Christoffel symbol is 0, and the other one contracts with the velocity as shown here. Okay, and I'm picking up only the spatial terms. I already got the time-like term, and so I've written it down there. Okay, so then again, I need my Christoffel symbols to bring this back to something I can recognize. So I need gamma I sub 0, 0. Okay, I have my explicit formula for the Christoffel symbols in terms of the deviation of the metric from the Minkowski metric. Okay, and here I see I'm looking for the large terms here. Well, first of all, the time derivatives on h's, they give me 0 because my problem is stationary. So the only possible term is this one. Okay, and this is a gradient applied to h00, but h00 was the gravitational potential. Okay, get my factor of 2, cancel that 2, get my factors of minus sign, get my factors of c squared, and there you have it. Okay, and then similarly, my Christoffel symbol upper I, lower 0j, I put in those indices here. A lot of the terms are 0. Well, this term is 0 because it's the time dependence of the h. Okay, but that's 0 because I'm a stationary field. Then I have gradients, spatial gradients applied to the coupling between time and space in the metric. Those are a's, and I put them in like that. Now, concerning raising, lowering indices, I'm in special relativity. Eta does the job, so eta 0, 0 is 1, and the spatial components are on diagonal spatials are minus 1, so you watch your signs. Okay, but I'll just put the indices appropriately to make things look conventional. And when I do this for my gamma, I get a very familiar friend of mine. I get the curl of A. That's what in electromagnetism I call the B field. So in this game, I'll call it the Gravito magnetic field. B is related to A by taking the curl. Over here, I see gradient of 5. Okay, well that's like in electromagnetism, the electric field is minus the gradient of the electric potential. Okay, so I cleaned all of that up. And what's my equation of motion? Well, it's the Gravito-Lorentz force law. Okay, so the acceleration from Newton's perspective is equal to the electric field plus a correction that's velocity dependent, goes like linear in the velocity and crossed into the B field. Okay. So then I can ask, okay, well, how special is the result? Well, it's not special at all, right? Velocity dependent forces are required by special relativity, where we're dealing with a problem with in linearized gravity, where I can think of the gravity field not as part of the metric, okay, but as part of a field which is propagating in a flat metric, in a Minkowski metric. So I could do all of these problems just going back to the first third of our course, where we derive the magnetism from the existence of electric field by doing boosts, of attracting or repelling electric point particles, and we discovered by boosting those configurations that there was a velocity dependent force, and the velocity dependent force was created by by the magnetic field, which came from a boosted electric field. Okay, and I can do the same game here, and I could have derived all of this in that particular way. I didn't do that because, like I say, I'm trying to move toward gravity, and we're getting used to Christoffel symbols and everything like that. But we could have done it that way. Okay, and it's a nice result. But remember, it's terribly restricted. It only works for linearized gravity, and it only works for non-relativistic motion in that gravitational field. So it's not nearly as general as the derivation of the Lorentz force law that we had in special relativity, because there we could consider any velocity up to the speed limit. Here we're stuck with small velocities, because otherwise we don't have the simplifications necessary to make the analogy. In particular, remember, one of the central ingredients in the Lorentz force law, okay, and the development of the Maxwell's equation, was the fact that the electric charge is Lorentz invariant. It's invariant to any change of reference. It's invariant to any coordinate change, okay? Okay, and that was the source of the electric field. In this game here, the source of the gravitational field is the energy momentum tensor, or in Newton's world, the mass density. Okay, and it's okay, and I get the simplifications that I got, that the energy momentum tensor, which is 10 components, reduces down to 4 components only in the approximation that the mass could be treated as an invariant. Okay, and so my velocities were necessarily small. Okay, and I could work the first order and no further than first order. Otherwise, the full tensor character of the source of gravity has to be dealt with. Okay, and that's the real general relativity. So I have special kinematic restrictions to play this game here, and it's an interesting game, and it brings out the velocity dependent in my forces, and I got some physics problems out of it too, some physics results. The lens tearing effect, okay, it can be attained without any knowledge of general relativity. Okay. It just follows from the velocity dependent of forces in special relativity. Okay, and that's what I stated here, and I talked about Lorentz invariance like that. So gravity only resembles electromagnetism for weak fields and non-relativistic velocities, and so it's curious. But of course, this doesn't. But of course, we're going to find velocity-dependent forces all over gravity, okay, as a consequence of special and general relativity. But there'll be higher order effects, there'll be nonlinearities, and there'll be some very interesting aspects which we want to discuss when we come to strong gravity and the rotating black hole. Okay. We certainly want to do the rotating black hole in this course because they're the most common ones in the universe, right? It's very unusual to find a star with no rotation. It's very unusual to find a compact object in the universe without any rotation. The evolution of stars, going through all of their cycles, supernova, and then compression into perhaps a black hole or a neutron star, involves all this dynamics that naturally enough generates angular momentum, and so you certainly expect that you want black holes described by their angular momentum, and that's what the Kerr metric does, and that's the subject of our next special topic, which we'll get to next time, and we'll find we'll find those interesting phenomena that we found in the Schwarzschild metric, except more so. We'll find event horizons. We'll find surfaces of infinite redshift, okay, and we'll find some astrophysical phenomena that goes well beyond what you could possibly do in the Schwarzschild environment. Remember, in the Schwarzschild environment, we had just one special surface, the Schwarzschild radius, okay, and it was a event horizon and a surface of infinite redshift. When you rotate the star, you're going to break the degeneracy between those objects. You'll have an event horizon which is distinct from the surface of infinite redshift, and that's going to create interesting phenomena which we're going to want to understand. We'll try to understand those phenomena in a generic way, and then we'll do a little bit of special work on the Kerr metric but there's a tremendous phenomenology there, and we'll leave most of that, of course, to more sophisticated developments. Okay, so till next time.